So, there is a table that is given to you. Okay. You are supposed to calculate the fractional or percentage contribution of Debye, Keesom and London dispersion forces to the Vanderwaals attraction for each pair of molecules at 298 Kelvin. Okay. So, what you have been given is you have been given different compounds ethanol, water, toluene, 3 cases. Okay. And you have been given what is the dipole moment, right, and the term that involves polarizability is given and beta is also given. Okay. So, that means if I take a container which has ethanol, okay, there are large number of atoms and molecules of ethanol, right. Okay. So, if I take a case like that, okay, what is the contribution of these 3 interactions to the total Vanderwaals interaction, right? That is the question. So, how do we go about doing that? So, with whatever we have discussed so far, do you think we can attempt this problem? Yes, no? Yes, right? Okay, let us look at this. So, this is if you have 2 identical molecules, right, 1 and 1, that will be the total Vanderwaals force of interaction, right. So, each of the terms, okay, as well as the oral interactions have the same x power minus 6 dependence, right. If that is the case, what I can do is I can take each prefactor, right, divided by this term beta, that will give you the fractional contribution of, okay, Debye, Keesom and London dispersion forces, right. So, if you go back and look at okay, then you can calculate each of them, right. So, that is the same term, right. So, every prefactor that you have here 1, 2 and 3, that divided by beta will give you the fractional contribution. Okay, let us try and calculate one by one. So, if you go back to the problem, so I have been given mu, right, the dipole moment, okay, that is given to me, okay, temperature is given, beta is given, okay, I can calculate this, right, 1 divided by 4 pi epsilon naught is 8.82 into 10 power minus 12, right, minus 12, it is Coulomb square per Newton meter square, okay, that is the unit, SI units, okay, that is whole square, okay, multiplied by 2 by 3 into, yeah,
1 by 4 pi epsilon naught is directly 9 into 10 to the power 9.
You can also use that, yeah, you can do that as well, yeah, yeah, 2 by 3 times mu 1, okay, mu 1 is given to be 1.73, right, is 1.73 Debye, okay, and you have to convert Debye into SI units. For that you are going to use a conversion factor which is 3.33 into 10 power minus 30, okay, that the unit will be Coulomb meter, right, it is a dipole moment charge times the distance, right, so that is Coulomb meter, okay, that is to the power 4, right, because you have mu 1 to the power of 4 there, okay, divided by Kb is 1.38 into 10 power minus 23, times 298, that is the temperature that is given, whole divided by beta 11, that has also been given to you, it is 3.4 into 10 power minus 77. Okay. Can you just work it out quickly and then let me know what the number that you get? Okay, so what's the number that you get? The number that I have is 0.427, what I have. Okay. There are a lot of exponents with very large numbers, right? So minus 77, you have 10 power minus 30 times 4 will be minus 120, right? Yeah. Yeah, point. Yeah, that's fine. Yeah, 0.41 is okay. I mean, you know, 0.41. Yeah. Okay. Anyway, so that's the order that you should get. Okay. So similarly, I can go back and look at FD, that is the Debye interaction, which is the interaction between a permanent dipole and a induced dipole, right? Therefore, you have a term that corresponds to the permanent dipole, right? That's the dipole moment, and the induced dipole, you know, there is a term that with alpha, which is polarizability. Okay. Therefore, so this is the fractional contribution to the Debye interaction. So, this quantity has been given to you, alpha naught divided by 4 pi epsilon is given in the table, multiplied by 1 over 4 pi epsilon naught, okay, mu 1 square divided by beta 1 1, right. So, 2 is here, 1 over 4 pi epsilon naught is this, alpha naught divided by 4 pi epsilon naught is given 5.49 into 10 power minus 30, that has been given to you, and there is again mu 1 square 1.73, 3.35, 10 power minus sorry, this is 3.33, 10 power minus 30 whole square now, okay, divided by beta which is 3.4, 10 power minus 77. Okay. If you work this out, the number that you should get is 0.097. Okay. So, let us go back, 0.097, that is 0.0, not that. Okay, this is 0.097. right, and this came out to be 0.427, right. Now, we want to calculate FL, right. We have done that, we have done this. We want to calculate what is the contribution of the London dispersion forces. So, how do we do that? So, you know this value, okay. What is that? Yeah, you,
1 minus
right, you can do that, right. FL plus FD plus FK should be equal to 1, right. The fractional contribution has to be 1. Therefore, 1 minus of 0.97, right, 0.427 should give you what is FL, right. You could have calculated it, but of course, you can get Planck's constant, but you do not know what is nu, right, but other parameters are given. Okay. But if you knew nu, I could have calculated it, but we do not know that. So, therefore, FL, what is FL that you get? Right, 0.476. Let us look at if our calculations are right. Okay, that was ethanol, right. So, we just calculated this to be 0.476, that is a percentage contribution, multiplied by 100 should give you 47.6, exactly the same number, right. You are again 9.7 and 42.6, right. So, similarly, you can do a repeat the same calculation for the other molecules that have been asked. So, one is water, other one is toluene, right. Okay. So, you can try and do a similar exercise. So, this basically gives you a feel for calculating numbers and and then see if you have done the right thing, right. So, because we are talking about fractions, so everything has to be less than 1, right, and all of them should sum up to 1. The total fractional contribution should show sum up to 1. Okay. So, if you know that, you should be able to get this out. Okay. Yeah. So, maybe we will stop here. So, what we are going to do in the next class is to look at if you have 2 blocks. Okay, we will do a simple exercise where I have 2 semi-infinite blocks. We will try and calculate the Vanderwaal's force of interaction between them, exactly similar way that we did for when we did the scaling arguments. Okay. We will try and work out an expression that we could use for calculating Vanderwaal's force of interaction between 2 blocks. Okay, that is what we will try and do in the next class.